Okay, so science begins with observation. Observation is the key tool of a scientist. So, you observe this plant growing in the Jewel Moore Nature Reserve. You observe it. Then the next thing is you'll ask a question. That question could be, is that a carnivorous plant? Because you haven't seen a plant like that before and you think it looks interesting, you think it might be carnivorous, so you ask the question. You look at it, you look at books and you look up other carnivorous plants, you look for evidence, and then you might come up with a hypothesis. And that hypothesis has to be a falsifiable explanation, right? So falsifiable means it could theoretically be shown to be wrong. So you wouldn't say, I think this is a plant that eats human souls, because we don't have a human soul measuring device. So that's not a valid hypothesis. But you could say, this is a plant that I think is carnivorous. So what we would do in Bio 1 or Bio 2 is write a research hypothesis. A research hypothesis is more than just your basic hypothesis. So in this example, in green is the hypothesis, or if you're colorblind, it's underlined, okay? So it says, this is a carnivorous plant. That's your hypothesis. That's your explanation for why it looks the way it does. Notice, though, that the complete research hypothesis has more than that. So it says, if this is a carnivorous plant, and I provide it with insects, then it will digest insects and absorb their nutrients. So we have, in purple there, we have a prediction of what will happen. We also have a statement of what we're going to do. We're going to provide it with insects. So a research hypothesis has three basic parts. The first part is your hypothesis, or your explanation. Okay? So if and then, it combines your hypothesis, your procedure, and your prediction. And that's the kind of hypotheses we will write in lab. That's why I'm introducing it here. So the pure hypothesis is simply, this is a carnivorous plant. But a research hypothesis would say, if this is a carnivorous plant and I provide it with insects, then it will digest those insects. That is a complete research hypothesis. Like if you were doing an experiment and writing a paper about it, you would include that in your paper. Another example, if my router is off and I unplug it and plug it back in, then my internet will work again. That's an example of a testable hypothesis. And it's falsifiable. You could unplug the router and plug it back in, and the internet might not work again. But remember, if your router is off as a hypothesis, you can't prove it right. It might be that it wasn't off. You unplugged it and plugged it back in, and it just so happened that at the same time, your internet provider flipped a switch and your internet started working again. So we have to be careful about using the word proved in science. But remember, hypotheses are your best explanation for an observation. They cannot be proven right, but in terms of science, when we can't show them to be wrong, we try really hard to show them to be wrong, but when we cannot show them to be wrong, we increase our confidence that they are valid. That's how science works. We try to show them to be wrong. When we cannot do that, it increases the probability that those hypotheses are correct. And remember, once again, as a scientist, you're always trying to prove yourself wrong rather than proving yourself right. It's easy to ignore contradictory evidence when you're trying to prove yourself right. But when you try to prove yourself wrong, you might be a little more honest about your findings. Lastly here, we design a controlled experiment now. We have a hypothesis. Now we design a controlled experiment in which we try to falsify our hypotheses. Remember, we don't try to prove them right. I just explained that because it's more honest. We will avoid our own internal biases if we try to prove ourselves wrong. It will at least make it more likely we will ignore those biases, or we will not succumb to those biases. What could we use for a control? We need a controlled experiment. Now, we might have controls for several variables in an experiment. Sometimes it's just one thing as the control. Sometimes you'll have many. But one example for a control. Let's say we're going to put a fly in a jar with our carnivorous plant. What would a control be? Well, we might take another jar and we might put a non-carnivorous plant in there and put a fly in it as well. Then after a week, we find what's left of the flies in both jars and we weigh them. And we mass them out and we see if the fly in the carnivorous plant jar has lost more weight. If they both lost the same amount of weight, then we can say, oh, the plant did not eat anything because the oak tree in this jar, we know it didn't eat the fly, and that fly lost just as much weight as the fly in the carnivorous plant jar. Or you might measure the fly in the carnivorous plant jar, and all you find are some feet and a dried out carcass, and the fly in the oak plant jar is still just fine. And you might say, oh, this is strong evidence that the fly was eaten. You could also take a piece of clay, the same weight as a fly, and put it in one jar, and put a fly in another jar with carnivorous plants in both. And you can see if the clay loses weight. Maybe things are just drying out. Maybe they're not being eaten. You can measure for that. You can think of a number of ways you can control the experiment. But what you're trying to do is leave all the variables the same, except for the one variable that you're trying to get at. Is this plant carnivorous? And that can take some thinking in order to develop a good controlled experiment. And I suggest you read about that in your textbook a little further, of course. But when we design an experiment, we have to make good observations, ask a clear question, a testable question with a good hypothesis, right? We want to do research on background as much as we can, predict the answer to our question, design an experiment, try to avoid bias at the same time. And other ways to avoid bias include having a big sample size. Why would a big sample size help us not only to avoid bias, but to get at the right answer? What if I wanted to measure the average height of a student on campus, and I grabbed one person at random and I measured their height, and I said, oh, the average height of a student on campus is 6'5" tall. Well, I just happened to have grabbed a tall person. Or I might say the average height of a student on campus is 4'8". Well, maybe I grabbed someone that was a little bit short. So increasing the number of samples increases the odds of you getting a more accurate estimate of reality. Also, we randomize our experiments as much as we can. So what if I said, well, I'll get 5 people's heights, 5 samples, and I go to the hypercenter to the basketball court during a time when the basketball team's practicing or something, and I happen to measure all the basketball players, and I say, well, the average height on campus is 6'3". Well, that's not an accurate estimate either. I had more samples, but they weren't random. So I need to say, okay, I'm going to throw a dart at a map of campus and throw 5 darts at the map, and I'll collect 5 heights from different people at those different locations. That would increase the odds of me getting a good sample of who is on campus. And we also have to have controls. Now, maybe there's not a good example of a control for measuring height, because that's not really an experiment more than it is just measuring. But if we were jogging, let's say, and we wanted to find out how jogging and weight loss were related, we would get a random selection of a bunch of people. So randomized, different male, female, etc., different people from different backgrounds. And then we would say, okay, one side, they're all going to eat the same amount of calories a day, let's say. That would be a control. And one group is going to jog and one group is not going to jog. And then we could look to see if one group lost more weight than the other. That would be an example of a controlled experiment. Now, once we've done a lot of experiments, we might fail to falsify a hypothesis. And that means we tentatively accept that hypothesis as likely true. Now, that does not make it a theory. We often use the word theory in science, and I want to give you an idea of what that means. In common English, we use it all the time, like, I have a theory that the light in my refrigerator stays on when I shut the door, or whatever. A theory is a well-tested scientific explanation that allows you to come up with lots of different hypotheses and test them, okay? It's a very broad statement, not a very narrow statement. Like the theory of natural selection is a very broad statement that allows you to make thousands of hypotheses and test them. So it's a very broad statement. And once something becomes a theory, that's as close to proven as it gets in science, okay? So theories make use of a lot of data from lots of phenomena. So in case of evolution, that'd be like fossil record, genetics, why humans have a tailbone, all kinds of things come together in a theory. It's as close to being proven, and of course theories can still be changed or falsified with new evidence. And so my question for you here is, name a biological theory. I'll name two for you. Evolution is one. Theory of evolution is a biological theory. And germ theory is a biological theory. That's a theory that diseases are mostly caused by germs. That's a theory. See if you can name another one. So in the next lecture, I will talk about the scientific method, and we'll move a little bit further through this chapter.